Okay. So, we have seen Maxwell relations that actually originates from the fact that the thermodynamic potentials, which are of course Legendre transformations of internal energy. So, the thermodynamic potentials being an exact differential give rise to 4 different Maxwell relations. However, as you know that there are many possible thermodynamic potentials are there, or many possible thermodynamic quantities are there. I can write some of them. For example, internal energy U, then Q is a heat, and then enthalpy, pressure, temperature, volume, Gibbs free energy, Helmholtz free energy, entropy, work done, and many other things. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let us say there are 10 different variables, 10 different variables or parameters. Now, once you write, when you write a particular partial differentiation, for example, dy by dx at a constant z, you need 3 variables y, x and z. So, therefore, I can take y as any of the first 10 and then x as any of the next 9 and then z as any of the next 8, giving me 720 possible partial derivatives. Now, once I take these 720 possible partial derivatives, and in order to equate with similarly more number of another set of 3 partial derivatives, there are huge number of partial derivatives that can be formulated, and therefore, in order to convert one partial derivative to another partial derivative can become a really humongous task or a very difficult task. However, why do we need to calculate such partial derivatives? For example, why do we need to calculate something like del g by del h at a constant t? Why do we need even these kind of quantities? So, you will see that, as I mentioned also earlier, that any of these partial derivatives ultimately can be cast into the few heat capacities that we discussed. For example, specific heat at a constant pressure, specific heat at a constant volume, then isothermal compressibility or adiabatic compressibility, and coefficient of thermal expansion. So, these are the quantities through which any of the partial derivatives can be expressed, and since those quantities are experimentally measurable, therefore, we can always relate to any of these quantities to those experimentally measurable quantities, because it is not easy to perform an experiment where we change the enthalpy of the system and calculate free energy at a constant temperature. It may not be possible, as we know that it may not be possible to directly measure an entropy of the system, and therefore, we need to calculate free energy at different temperatures in order to get the value of entropy. So, something like an indirect relation. So, in order to do that, we have to know how to break these partial derivatives like this what I mentioned into those heat capacities, and thereby we can estimate experimentally those partial derivatives, and therefore, this particular subject of conversion of partial derivatives or transformation of partial derivatives is very important in thermodynamics, and we are going to discuss that today. So, in the textbook there are standard techniques, often I find it very difficult to convert one partial derivative to another. However, I encountered a software like Mathematica, which I talked to you before, that it can convert partial derivatives to one form to another form very easily. And when I looked into that, and I will show you in a moment that thing, how to convert one set of partial derivatives to another using Mathematica. When I encountered that, I tried to find out the logic behind it. Remember, Mathematica is just a computer program, and therefore, it must have a very definite logic by which it can convert one form to another form. And I saw that it follows a procedure called Jacobian technique. Jacobian technique or Jacobian method of conversion of partial derivatives. And we are going to talk to you about that. This method is not so popular in books, however, there are papers associated with it, and I am going to show you the paper, and also I am going to show you the conversion of partial derivatives using Mathematica briefly. So, okay. So, this is a paper that can be followed on the use of Jacobian in thermodynamics by Benjamin Carroll, and this came in the Journal of Chemical Education. This is the technique that I am going to discuss today for conversion of partial derivatives, and you can refer to this particular paper in order to refer to this method in more detail, and I am going to show you also using Mathematica that we can convert that. Okay. So, you see I am opening something equivalent to Mathematica called computable document format, which is freely available. You do not have to have a license or anything. So, there you can also test it. For example, you can look at a particular partial derivatives written as. So, as you can see, this is a partial derivative of dE by dP at a S, which is you can show you here, dE by dP or du by dP at a constant S. Once you do that, you get beta P V C V by C P. So, beta is again isothermal compressibility, as I see. Let me see what is mentioned at beta. See, coefficient of thermal expansion is alpha and compressibility is beta. So, beta is compressibility, which is you know as minus 1 by V del V by del P at a constant temperature. So, isothermal compressibility, and sometimes it is also written as kappa T, I mentioned as kappa T, and alpha is coefficient of thermal expansion, which is 1 by V del V by del T at a constant P, and P V are just pressure and volume, and C P and C V also as specific heats. So, you can see that the change in internal energy E as a function of P is at a constant S is nothing but this particular quantity. All of them are measurable, and therefore, one can measure this particular partial derivatives. So, if I change it, I can also show you some other example. So, if I change E to let us say something like G, and if I change the pressure to something like S, and if I take it at a constant V, I get to see another different expression as mentioned here. So, Mathematica can quickly calculate that. I can also take del P, and I can show you some of the Maxwell relations. So, for example, I can show you del S. So, del S by del V at a constant temperature. So, we know that del S by del V at a constant temperature is nothing but del P by del T at a constant volume, and that is coming as alpha by beta, which is alpha by kappa T. So, you know that del S by del V at a constant temperature is del P by del T at a constant volume. From this Maxwell relations, we can calculate that del S by del V at a constant temperature is del P by del T at a constant volume, and that is coming out to be alpha by kappa T. So, let us see del P by del T at a constant V also, del P by del T at a constant volume, and that is also alpha by kappa T. So, you can see that whatever the Maxwell relation gives, thermodynamic relation also gives the same thing. So, now we have to find out a general way to get all possible partial derivatives, and that is what we are going to discuss today. So, first of all, we want to understand what is Jacobian. So, let us see what is Jacobian. Jacobian is something that changes the variable from one to another. For example, f x is x square, and I want to convert it to a function, another function of z. So, I want to change x to z. So, let us say I write z as x square. So, in that case, if I take the derivative of z, I will write that dz as j Jacobian into dx. So, Jacobian is the quantity that will convert one variable to another variable. So, what will be the value of z? So, let us take a derivative of this particular equation 1. So, dz by dx we know is 2x. So, therefore, dz is nothing but 2x dx. Now, when you compare equation 3 with equation 1, compare 2 and 3, what do we get? We get Jacobian to be 2x. So, the Jacobian is something that again, as I said, convert one variable to another variable, and therefore, we can write that f x function as some, we can convert f x to some g z function, where my g z will be just simple z, because I am converting just x square, I am mapping f x to another variable z, and whenever we want to take a derivative of that, we need to use the Jacobian form. Now, we do not use the Jacobian in for the first when the function is dependent on one variable only, then we do not need to use the Jacobian, because you can get directly by taking the derivative with respect to the function. But let us say I have a function that depends on two variables. Often we know that our function u or internal energy u depends on, let us say, two variables x and y. When that happens, we know that we can write du as the total differential as del u by del x dx at a constant y, of course, dx plus del u, and I am writing u as a small thing, not, it does not necessarily mean that it is the internal energy, it is just some function u, just a function u of x and y variables. So, del u by del y dy. So, u is a function, and also let us say v is also a function of x and y. So, I can write dv as del v del x at a constant y plus del v del y x dy. Now, I get equation 4 and equation 5. At this point, you need to know something called matrix multiplication. So, if you do not know matrix multiplication, you do not have to worry, because we are not going to talk about too many variables, we are going to talk about only two variables only. Okay, I forgot to write the dx. So, now we have these two. Now, you need to know matrix multiplication. So, I will just briefly tell you about matrix multiplication. So, let us say I talk about 2 by 2 matrix A11, A12, A21 and A23, and when you multiply with, let us say, two variables x and y, then we have to multiply this way. You go, I will just draw with a different line, this way, and for so if I multiply this matrix, so this is 2 cross 2 matrix and this is just 2 cross 1 matrix, that will give me 2 cross 1 matrix, and if I write that, it will be A11 x plus A12 y, one term, another term will be A21 x and plus A23 y. So, there also I am going this to this and plus this to this, that is simple matrix multiplication. So, if I use matrix multiplication, it is very easy and convenient to write multiple variables in a matrix form. So, I am going to write this equation 4 and 5 in the matrix form as this. So, du by du and dv, these are two variables on the left hand side. So, it is a matrix of 2 cross 1, and right hand side I have a matrix of this 2 cross 2 terms du by dx y, du by dy x, dv by dx y dV by dy x, and then I have this dy dx and dy. Okay, I will just put a line here in order to denote the separation of the space. So, you see I got now a matrix form of an equation. This is typically called vectors. This is matrix and this is also a vector. So, what essentially we are doing is that I have this pair of variable x and y, which I am converting to a pair of variable u and v. That is what we are doing, and this is the Jacobian matrix. If I had only one variable, you see it will reduce down to only one term. So, if I did not have two variables, then I will get just one. As you can see, I will get, let us say du, and let us say there is I am converting u to x, I will simply get du equal to du by dx dx. So, for one variable, for a single variable, let us say u going to x, I will simply get du equal to del u by del x dx. So, you can see for 3 variables I can get 3 by 3 matrix, 4 variables 4 by 4 matrix and things like that, and I will get a Jacobian matrix, and using that Jacobian matrix it will be helpful really to get the desired changes in thermodynamic variables. How, that we are going to discuss. Before we do that, we will discuss some notations. One notation is that this matrix that we talked about, Jacobian matrix, can be written in a much simpler form as this one. So, this means du by dx constant y, du by dy y at a constant x, and then dv by dx at a constant y and dv by dy at a constant x. Whatever the Jacobian matrix we discussed, this is our Jacobian matrix. So, this is just a shorthand notation. Till now we only know dy by dx kind of thing, but here you see I am using a pair of variable duv by dxy, and that I have to write in this form. So, you can see that immediately some properties will come up. Let us say if v equal to y. So, what will happen? So, let us call that as equation number 6. So, if v equal to y, then from 6 what we will get is d uv by del uv by del xv, and I will write it on the right hand side del u by del x, v equal to y, right. So, y del u by del y x del y by del x. If I say v equal to y, then I can write dv as y, and then I can write that as del y by del y x. Now, you see what is the consequence of this particular thing? dy by dx at a constant y is nothing but 0, and this dy del y by del y is nothing but 1. So, again in the matrix multiplication you have to multiply these two corners, for example, a11, a12, a21 and a22. The matrix multiplication product will be this minus this. So, it will be a11 into a22 minus a12 into a21, that will be the multiplied product. So, similarly, here what will happen is that it will be del u del x fixed y into 1 minus 0 into del u by del y at a constant x. So, it will give you del u by del x at a constant y. So, only thing is that I would like to change this v to y because we said v equal to y, which means that either I keep v or I keep y. So, I kept y. So, you see what just happened, if the second variable. So, for example, I was converting earlier x y to u v, now I am converting x y to u y. So, instead of two new variables, I have introduced only one new variable u. In that case, it is simply the partial derivative. So, we can always write the partial derivatives in terms of Jacobian like this. So, I will give you an example. Let us say I am talking about del p by del t at a constant v, which is in this particular form. Then I can write in this particular form as del p v by del t v. Okay. So, this is very important, because we need to convert it again and again to this kind of format. Okay. So, now second rule is element interchange. Let us say I have d u v by del u v by del x y. If I interchange u and v, it will become v u minus of del v u by del x y, and that interchange basically happens due to matrix rule. You know, in matrix, if we change one row, then the determinant becomes. So, this Jacobian is a determinant, by the way. This Jacobian matrix. So, but the value Jacobian is the determinant. For example, here we are writing as determinant, and this is the determinant of this particular matrix is this one. So, this is determinant, just matrix product. Once you understand this rule, you will see that later on it will become very easy, but right now it might be little bit learning curve for some of you. So, now you see, when you interchange the element, v becomes u and u becomes v, we are essentially interchanging the rows. So, v becomes u and u becomes v, means I am interchanging one row, and the rule of the matrix is that the determinant will become negative, and that is why it becomes negative when you change that. So, now we are going to use chain rule. Okay, so, I will just border it, I am going to use the chain rule now. Chain rule says that del u v by del x y can be written as del u v by del new quantity r s, a new variable, multiplied by del r s by del x y. So, often it may be necessary to introduce two more new variables, often it is let us say p t. So, I can give an example for that. Let us say we are trying to convert del g h and del v t. I can always write del g h by del p t multiplied by del p t by del v t. See, it is not necessary that you need to completely change both r and s, you can change one of them, and that is what we have done here. So, this is an example for the above chain rule. And then the final one is reciprocity. Sorry. Then the final one, reciprocity. Del u v by del x y is inverse of that, which means del x y by del u v to the power minus 1. Okay. So, once we have that, we now need some steps. Okay. So, I will just border it also. So, we talked about reciprocity, we talked about chain rule, we talked about element interchange, and we talked about that if one of the variable is less, like instead of 4 there are 3, then we can write like that. So, once we have that, now we are going to tell you the steps of reduction. Of this variable. So, first of all we will talk about step 1, steps of reduction. Now, there are some rules for reducing the thermodynamic variables. So, we are going to do that. So, for example, if the thermodynamic variables contain some this thermodynamic derivatives contain some thermodynamic potential like G and U and all. So, bring it to the numerator. So, bring the thermodynamic potentials to numerator. For example, if you have del T by del P at a constant G, you can write that as del T G by del P G, okay. And then you can write that as write that of course as G T and del G P, because we are converting both then in the numerator and in the denominator. So, negative cancels G P, sorry, and then you can introduce a new variable, let us say P T, and then you can write P T by del G P, and then you can write del G by del P at a constant temperature. So, you have brought G to the numerator, and here you can write that as del G P by del P T to the power minus 1. You can write even more, you can write del G P by del, okay. So, you can write that as T P, but with a minus, and that is there is an inverse sign. So, you can write del G by del P at a constant temperature, and this one you can write as del G by del T at a constant pressure. Of course, there is a minus sign and inverse of that. So, you see that we can bring the thermodynamic potential to the numerator, because that will help, because many of the derivatives contain where the thermodynamic potentials is at the numerator. Now, step 2 of the reduction. That write the derivative of the Jacobian notation, that is the already I discussed, write the derivative in Jacobian notation. For example, if you have del T by del P at a constant volume V, you can write that as T V by del P V. Remember, we showed that if one of the variable is same, then it will come like that. So, you can show that. Now, step 3, introduce P and T as independent variable. You will see it is extremely beneficial to introduce these two variables as independent variables, because many of the heat capacities use P and T. So, for example, if you have del T by del P at a constant volume, you can write that as del T V and del P V, and then you can have del T V and then del T P, you can bring it, for which you have to multiply with T P and you have the P V, and you will see immediately you will get some interesting thing. So, it can be written as V T by del P T, and this can be written as minus of del T P by del V P. So, now you know this one is del V by del P at a constant temperature, and this is minus of del T by del V at a constant pressure. Now, if you identify this quantity del V by del P, you know that 1 by V del V by del P is compressibility, right, isothermal compressibility, which is kappa T. So, this is nothing but V into kappa T, and this one is del T by del V at a constant P. It is just inverse of del V by del T at a constant P. So, this is you can see that it is minus of V into coefficient of thermal expansion, and of course, we have taken inverse of that. So, this is minus 1 V into alpha. If you see, it is minus kappa T by alpha. So, that it becomes very easy when you do that. So, now step 4. Okay. So, step 4 is once you write that, of course, step 4 is obvious, that convert the Jacobian back to partial derivatives, which we have done, as you can see here, from this step to this step we have done that. Okay, so, I will give you a convert back example. The example is, let us say you have del PV, and let us say you encounter this kind of situation. That means, it is nothing but del P by del T at a constant V, which we have used above. And then step 5, the final one. So, using the definition of the heat capacities, relate the partial derivatives to those. For example, here we have identified that, here we have done that these quantities are that. So, these are the rules of Jacobian, and once you have the rule, you can convert more and more difficult partial derivatives to change from one form to another form, and we are going to give you an example of that.